So this is the second midterm, really the first major midterm of the course. The first midterm occurred before in January. You've seen the video for that by now. And all I'm trying to do today is talk about that, sort of really ultimately come down to what are we looking for and why do we feel it's important. So in terms of what we had on that question, and I just want to highlight some things here. We had, well, maybe I'll start with the question and just sort of work through it. Collar mass 0.75 kilograms, so that's that collar right here, is sliding along a semicircular rod of radius 90 millimeters as shown in the diagram. A spring with K equals 160 newtons per meter and an unstretched length of 120 millimeters is connected to the collar at one end and is pinned at point A at the other end. Coefficient of kinetic friction between the rod and collar is mu K equals 0.2. Gravity acts downward as usual at 9.8 meters per second squared. At the instant shown in the diagram, the collar has a speed of 3 meters per second and theta equals 50 degrees. So you got to be careful. This is a lot of information. So we have A. We have the origin, we have the mass, we have the spring, and the spring goes across this entire diameter or partial diameter. This is the diameter of the circle. So the spring is fully stretched here, and it's going to be at zero stretch over here. Draw a free body diagram of the collar showing all the forces and directions indicate angle theta and alpha in the diagram. You need to provide the numerical value of alpha in the figure. Determine the normal force on the figure on the rod acting on the collar. Determine the acceleration of the collar in XY coordinates. So one thing I should mention at this point, this was the first exam that we gave during the coronavirus last year, or well, in 2020, and so this was kind of different expectations maybe. So in terms of figuring out what the length of this spring is, I know one thing, and that works out to my favor, which is that this distance right here is R, and this distance is R, and that sort of spans the entire length of the spring. So I have two right triangles I can work from with, right there. Theta equals 50 degrees, and I can say that theta or the included angle right here is 25 degrees. So I can rebuild my I can rebuild the diagram and sort of get my stretch distance. So if I look at the various forces here, I have a normal force which is pointed outward. I have a friction force which is pointing in the opposing motion. I have spring force which is acting outside of this line, and I have a normal acceleration and a tangential acceleration. I'm using NT coordinates in this. So in terms of force normal equals mass times acceleration, I've got the weight component from this figure. I've got the normal component, and I have the force of the spring cos alpha. Now, it's positive because the direction normal points in towards the center of curvature, and that equals mv squared over rho, which is man. Whoop, right there. So force normal is equal to the remaining terms. Force of the spring I can calculate from that stretch. We can add all the terms up together. And I end up with force normal for all of the rest of the terms is equal to negative 63.1 newtons. Force tangential is equal to mass times acceleration tangential. I have all of the forces there, and I have an acceleration diagram that I'm showing there. Acceleration tangential, then I can calculate from the remaining terms. Acceleration tangential is shown there, and I get for spring sine alpha minus mg cos theta minus mu sub s f sub n over m. Substitute all the numbers in, and get all the terms together. Each of these is just a calculation of the individual terms. I get an acceleration tangential of minus 19.2 meters per second squared, so it's decelerating. Or an acceleration which is minus 19.2 in the tangential direction and 100 meters per second squared in the normal direction. tan of beta based on that, taking the 2 and dividing them, you get 10.87 degrees, and that's my angle between the acceleration and the acceleration normal. And then I can rewrite that as a total acceleration of 101.82 meters per second squared. So I take just these two terms, square root it, and that's 10182. I can also say, look, if I know this angle and I know this angle, then acceleration x is going to be 101.82 cos 60.87, and acceleration y is going to be the sine of that term. And so I end up with acceleration, which is minus 49.57 I minus 88.95 J meters per second squared. This is another one, an owl, bird of mass 9 kilograms, begins to dive straight down at 50 kilometers an hour and falls freely in gravity. There's a drag force exerted by air on the bird. If the bird reaches a downward velocity of 200 kilometers an hour after falling 1,400 meters, force, velocity, and distance, how much work is being done by drag force? If the bird reaches a downward velocity of 200 kilometers after a 10-second dive, then that's force, velocity, time. What is the average drag force? And if force drag is a function of speed, then what is the maximum dive velocity that could eventually be attached or attained by the bird? And this is a little bit intuitive, but acceleration is equal to 0 meters per second squared when it's at its maximum velocity. It can't go any faster. So that's where how you calculate that. So you have first a work energy, then an impulse momentum, and then you have a typical kinetics problem. So summing forces in the direction for A, you have mg minus force of drag. So you can do, this is probably not a V here, it should be a U. So T1 plus sum of work 1 to 2 equals T2. You have the initial kinetic energy, you have the final kinetic energy, and the work done here by gravitational forces and the work done by drag forces. Drag is negative because drag is opposing motion. Weight is positive because it's in the direction of motion. So work done by the drag force, if I solve through for all the remaining terms, I end up with minus 35,109 joules, just substituting in terms. If I take the impulse momentum, so for 10 seconds this occurs, do the same thing, but now my integral is the impulse momentum expression right here, and that's over some time. I will get a force of drag of 50.23. So for the third part of this, we really have just the bird which is diving down. And so if you bear with me, a bird that dives down kind of looks like this if you're not an artist. You have a force of drag which is acting upwards, and you have weight which is acting downwards. And so to balance that out and to have a terminal velocity, acceleration in what I'm terming the x direction is equal to 0 meters per second squared. So force of the drag equals weight. Force of the drag equals weight becomes this relationship, which you're given at the very beginning, 0.009 v squared, equals mass of bird times g divided out, and you end up with 99 meters per second. The next problem that you have is the first problem that we've looked at in terms of kinematics, rigid body kinematics, and that's a 3-bar linkage, BC, CD, AC. BC is 3 meters, CD is 4 meters, and AD is given as 1.5. At the instant shown, BC is horizontal, parallel to the x-axis. AD has an angular velocity. And angular velocity positive means that it is counterclockwise, which means it's in this direction, and a angular acceleration of minus, so that's your omega, and your alpha is in that direction here, minus 5 rads per second squared. Find the velocity d in xy coordinate, magnitude of the acceleration d at point D, 10 marks, distance from D to the IC of zero velocity of the bar CD. Show your work with a neat sketch, and the magnitude of the normal acceleration at point D. Point C, pardon me. Okay, so if we start with this, we have omega AD of 2.5 rads per second, alpha AD, which is minus 5 rads per second. So we have velocity of D, which is omega R, which equals 2.5 times 1.5, which equals 3.75 rads per second. I've got that directly. Velocity D in the x direction, based on this diagram right here, I've got a 30-degree angle. Cos 30, 3.25 meters per second. And for y, it's going to be acting downward. So I have a typical x, y, and here. And so it's minus 1.87 meters per second. So my acceleration at point D is going to be 12 meters per second squared, because I add square each of the components, square root it, and I get the total value. For the instantaneous center of zero velocity, this is kind of, it works out really nicely because these two lines sort of correspond well. And this is one of those cases where the IC sort of works well. So here I kind of expect it to either go up or down, but because I know this is the direction, I know that everything is rotating here. And so my final velocity at point C is going to be upwards. And the distance from C to D and D to the IC is D to the instantaneous center is 2.31 meters. And to find velocity of C, I can calculate velocity of D, and I will get 1.623 rads per second for omega CD, about the instantaneous center. Velocity of C is 7.5 meters per second. Or the other, to calculate the same value, velocity of C is 7.5 meters per second. For point C, horizontal acceleration equals normal acceleration, and so the magnitude is just going to be v squared, or vc squared, divided by its length, which is 3 meters, or 18.75 meters per second. It's a broad range of material. It's not everything, but this is the first half of the course, and it's the first introduction in the exams looking at rigid body motion and rigid body kinematics. Thank you, and we'll talk.